Okay. Students, for this lecture, we have been talking about amphibolite to granulite transition, low pressure. We are talking with respect to mafic rocks, of course. And then we have low pressure granulites, intermediate pressure granulites, which are garnet free. And then you have high pressure granulites, which are garnet bearing. And then at still higher pressure, where orthoperoxine is taken out, you have garnet clinoperoxine plagioclase assemblage. And even at higher pressure, plagioclase is exhausted out, and you get, through the breakdown of jadeite component, albite to jadeite, and you get eclogite components where plagioclase is absent. So we have done this. But, you know, in order to understand reactions, we metamorphic petrologists use something which is called chemographic relationship. Chemographic relationship. That is chemographic relationship. These are important to find out reaction relationships, which assemblage is at what variance, etc., etc. And that is a very complicated thing. It has a very strong thermodynamic bias, which most people don't know. Normally, a typical diagram, I can tell you, you must have been, your teachers must have told you. Say, for example, AFM diagram, AKF diagrams, ACF diagrams. These are the common diagrams that are suggested to you. So these are essentially projections of compositions of reactions and then trying to figure out what reactions may have operated, etc., etc. Now, before I think I will go back to the lower grade metamorphism of amphibolites, which involves quite complicated minerals like chlorite, amphiboles, I think we should understand a little bit about these projections. Otherwise, it becomes a little boring to understand, and maybe you will not be able to understand. So, as a foundation to that, I will tell you the basics of chemographic relationships. I will tell you a little bit about AFM diagrams. And then we will move over to mafic rocks, where I will show you how multiple projections is done in order to understand chemographic relationships in complex chemical systems. Now, I will just introduce the subject with respect to pellitic rocks, because many of you may be familiar with this, but later on we will do, in the next video lecture, we will do a more complicated phase diagram. Chemographic relation, which is, superimposing one on the other. The essential thing of a chemographic relationship is the following. Normally you have a screen. Normally what happens, you have a screen. And you have a source. It's very similar to a source of light, which through electric currents, a source of light, and an object. It is very similar to this. Say, for example, if this mobile here, if I had lighted this thing, this would have been a source of light, and I, myself, is standing here. So if there is light on the background of it, which is the screen, you will see a shadow of mine. Now that shadow is three-dimensional particle, quite a fat one, 3-dimension, and then at the back, it's 2 dimensions. So essentially what is happening is, you take a source, you project a volume onto a plane so that you reduce the number of components, dimensions. I'm 3D, this is 2D. So, because we always are in a plane, we see things better on a plane rather than on space. So, chemographic relationships essentially involve projection of a complex chemical system into a relatively simplistic volume, or especially on a piece of paper on 2 dimensions, where we can see the chemographic relations are done. And sometimes what happens, say here is the source, I'm an object, there is a shadow, and from that shadow I take another shadow on it. Have you understood? So I take the shadow as a source and project it onto another plane. So you can have more and more projections, and you see complex relationships in complex systems, mineral assemblages, shrunk to smaller and smaller planes so that you can see the relationships much better. This is the basis of demographic relationships, and it's a very, very powerful tool. But in order to do that, the most important thing that you should remember is you should maintain 5 rules. Normally, this is not what is taught. You have to have 5 rules that are important for any projection. If multiple projections, then these rules apply multiply to others. But don't get afraid, it's not so complicated. You need a little bit of gray matter somewhere up here. And you can do a very good work on this, and it does a great amount of service to your understanding about metamorphic relationship. Now, I will tell you the rules, and I will advise you that you take out your notebook and your pencil. Take out your notebook and your pen and keep it with you. When I tell a rule, you write it down. Rule 1, Rule 2, Rule 3, Rule 4, Rule 5. The derivations I will do in the book. So essentially we start with the source, and then we project a 3-dimension into 2-dimension, a 2-dimension into 1-dimension. Say for example in structural geology. Why do you use stereographic plots? Why? The simple reason is all data that you have in planar and linear structures are in 3 dimensions. Essentially with the stereographic projection, what you do, you project it onto a horizontal plane. So your plane becomes a line becomes a point. That's also what you do in crystallography. In structure, we do south hemispheric projection. If you do it in crystallography, it's north hemispheric projection. But essentially, the thing is the same, that you're projecting 3D to 2D and in 2D to 1D if possible. In metamorphism, we do successive projections so that you can see the phase relationships much better. But essentially, for projection, you should have a source, you should have an object, and you should have a screen. These are the 3 things. You've got to have a source from which you project, you should have a material which is being projected, and you should have a screen where the shadow of the projection is planted. And that is important. What you do essentially is, when you try to project, you see, I'm a 3-dimensional person. If you project me, my shape is going to change. If your light is like this and my shadow is like this, it will be distorted compared to that if I was normal. If I move on to that side, it will be slightly more distortions. So the more you project, the more distortions you will do on the chemical composition of it. Because obviously you're approximating things. But nothing should happen to the variance of the assemblage. We try to do it in such a way such that the variance of a particular assemblage is not changed. And that is where thermodynamics comes in. So you should have a source of projection point. You should have something that you want to project. And another thing, you should have a projection screen. So before we go into I will dictate a sentence and you write it. I want you to write. I could have written it here, but I want you to write it. The variance of an assemblage. This we have discussed threadbare in many classes, but just a summary of it. The variance of an assemblage of minerals is defined as the number of variables that can be independently changed without changing the assemblage. Without changing the assemblage. Once again, I will repeat. The variance of an assemblage of minerals is defined as the number of variables that can independently be changed without changing the assemblage. This is the cornerstone of any chemographic projection. Whatever you do, you don't change the variance of the assemblage artificially. Don't change it. But you can do some valid approximations. And these are the rules. Now you write down rule 1. These are simple rules. I will do the derivation on the board. Rule 1. Components that occur as pure phases. Components that occur as pure phases, such as SiO2 in quartz, TiO2 in rutile, need not be plotted. Need not be plotted. Rule 1, once again. Components that occur as pure phases, such as SiO2 in quartz, TiO2 in rutile, need not be plotted. What does this mean? So this is rule 1. Why shouldn't it be plotted? We come to that question. I will do it two ways. I will do it using the Gibbs-Duhem method. This is the Gibbs-Duhem equation. For quartz, STT, VDP minus NSiO2 minus into DFUSiO2. Now, if SiO2 is pure, activity is 1, mu SiO2 is equal to 0. Right? So this term essentially vanishes because activity of SiO2 in quartz is equal to 1. So it's not a variable. In other words, we can write it this way: G SiO2 quartz at pressure temperature is equal to G0 quartz PT SiO2 plus RT-ln activity of SiO2 in quartz. If quartz is a pure phase, if SiO2 in quartz, rutile is a pure phase because it's TiO2 in quartz, so the activity of SiO2 in quartz is equal to 1. That means GSiO2 in quartz is equal to G0 quartz SiO2. Means what? The free energy of SiO2 at any pressure temperature is equal to the free energy of the pure phase. So either you can use the Gibbs-Duhem equation or you can do the free energy equation. It doesn't matter. So if you have a pure phase like SiO2 in quartz, TiO2 in quartz, if it's a pure phase, you can simply do not need to plot it. You do not need to plot it because you do not, if you do this approximation, if you don't plot, the variance just doesn't change. The variance still remains temperature and pressure. d mu SiO2 is not a variant because it becomes 0. Derivative of a constant is equal to 0. Same here, activity of SiO2 in quartz is equal to 1. So the GSiO2 in quartz is equal to the pure SiO2 in quartz. Remember, this is a function of pressure and temperature. Same as here. I didn't say dt or dp is equal to 0. Right? So that is rule 1. Now let's do rule 2. This is a very interesting rule. Now, components, remember the words, write down. Components whose chemical potentials are controlled external to the system. Just remember, externally controlled fluid systems. So once again, components whose chemical potential are controlled external to the system need not be plotted. Need not be plotted. So, something like, let's say there is a fluid and there is H2O and CO2, and XH2O plus XCO2 is equal to 1. You know the derivation, dxH2O is equal to minus dxCO2. That's the derivation. If you go to Gibbs phase rule, what happens? S dt, S fluid, into dt minus V fluid in dP plus sigma mu r, I will write the NCO2 first. NCO2 d mu CO2 plus NH2O is equal to d mu H2O is equal to 0. That is the Gibbs law equation for the fluid, where the fluid is composed of H2 and CO2. Now what is the problem? The problem is components whose chemical potential are externally controlled. Externally controlled means it cannot it cannot vary. So mu CO2 and mu H2O, they can't vary. So if they can't vary, they are constants. So if they are constants, the derivatives are 0. So if your chemical components are externally controlled and that external control source does not allow it to change, then both of these mu H2 and mu CO2 in the fluid, their numbers don't change. So they are not 1 like rule 1. They are not 1 like rule 1. In rule 1, what was there? SiO2 was a pure phase. There is not a pure phase. H2O is a fluid between H2 and CO2. But it is externally controlled. So if it's externally controlled, H2O-CO2 ratio does not change. So if H2O ratio does not change, this whole term is equal to 0. And therefore you have the normal variables, pressure and temperature. So that is the insight into rule 2. So if fluids are externally controlled, then you need not plot them. So any chemical potential, here I have taken the example of a fluid. If any chemical potential, say for example, d mu K2O in some reaction, d mu K2O. If K2O is externally controlled, d mu K2 is 1. D mu K2 is 0, it doesn't change. Now we come to rule 3. Components occurring in only one phase need not be plotted if we also ignore the phase in which the component occurs. I will repeat again. Components occurring in only one phase need not be plotted if we also ignore the phase in which the component occurs. This is very interesting. Looks very complicated. No, it's not complicated. It's very easy. It's very easy. Say, for example, let's take something like Ca3PO4 phosphate. Is this right? Appetite formula. Say we take appetite. Ca3PO4 voltage. I think it should be. Huh?
Ca5PO4 whole 3.
Yeah. Ca5PO4 whole 3. Calcium valence is 3. CA5PO4 whole 3.
And then you have a FClOH.
Ah. Just a moment, please. Okay. CA5PO4 whole 3 OH, no?
OH, F and C.
Yeah, it doesn't matter. It's primary. Now let us come to this. Now, say for example, if you have seen thin sections like pellets, metabasic rocks, quartz feldspathic rocks, apatite is very common. Apatite contains phosphorus, or it also contains P2O5. But if you have looked at all minerals, none of them contain phosphorus. None of them contain phosphorus. Say in pellitic rocks, or in mafic rocks, or in quartzo-feldspathic rocks, there is hardly any mineral which contain phosphorate, except possibly from monazite. So what happens is, if you drop phosphorus as a chemical component, and you drop apatite as a chemical base, so you have F is equal to C minus P plus 2. If you drop calcium, then you reduce the component by 1. If you drop the phase, then you reduce the component by phase. So the variance of the assemblage remains the same. That is why you have rule 3. What is rule 3? Components occurring in only one phase need to be plotted if we also ignore the phase in which the component occurs. Can you tell me a mineral, similar mineral like this? I'm asking my student. You know this, you have worked with this.
Zircon.
Yeah, zircon is another mineral. Say for example zircon, ZrSiO4. Zircon does not occur in any other mineral. So take out ZrO2, take out zircon. No change in values. Or something else, more complicated mineral than zircon.
Tourmaline.
What is the element that you should throw away?
Boron.
Boron. Boron occurs in tourmaline, commonly occurs in tourmaline. But if you don't want boron, take it out of the component, drop tourmaline, you're done with it. Your valence remains the same. So you drop a component, you drop a phase, and what is rule 3? So components occurring in only one phase need not be plotted if we also ignore the phase in which the component occurs. Right? Now we come to rule 4. What is rule 4? Components that are not sufficiently abundant. Components that are not sufficiently abundant to stabilize a mineral can be ignored. Components that are not sufficiently abundant to stabilize a mineral can be ignored. Say for example, I will give you an example of rule 4. Say for example, I have SiO2, this is quartz. Normally what happens in some cases, the silicon 4 plus is replaced by sodium plus Al3 plus. And this substitution of silicon by sodium and aluminium occurs in extremely low amounts. Have you understood? Extremely low amounts. So, say for example, if I write GSiO2 quartz is equal to G0 SiO2 quartz, PT conditions at PT, same equation plus RTLN activity of SiO2 in quartz. Now listen. In quartz, the amount of sodium and aluminium occurs in parts per million range. In the range of parts per million. 10,000 ppm is equal to 0.01 weight percent. 10,000 ppm is 0.01 weight percent. So, if you have a SiO2 quartz where you know that you have been able to detect sodium and aluminium, but they occur in such a small amount that the activity of SiO2 quartz is approximately equal to 1. Otherwise, it may be 0.9999999 reckoning. So if this goes on, then you can understand the effect of this on this GSiO2 is equal to G0SiO2 must be very, very small. So that is why it says components that are not sufficiently abundant to stabilize the mineral can be ignored. Can be ignored. So that is what, if there is a component which is, say for example, we have a mineral which is quite famous because it can be dated ZrSiO4. Now here you have silicon 4 plus and zircon 4 plus. Sometimes this is replaced by Ti4 plus. Do you understand? But if the titanium content is not so high, then you take the certain saturation without titanium. Although their variation is now found to be a temperature indicator, but whatever is that, even 10 years ago, titanium would have been completely discarded. So what happens if there is an element which forms a part of the mineral but is not sufficiently abundant, so the activity of the main component, or here SiO2, is so high, then the other component can be ignored because it does not create much of a change in variance. Because if it did, then this would become a variable. So not only pressure and temperature, but activity SiO2 will also become a variable. But if the abundance of the contaminant is very low, then you can take this as equal to 1. It's as simple as that. Now you see, so this is rule 4. We will come to rule 5 later on. We have finished rule 4, no? Yes, we have finished rule 4. We will come to rule 5. But before we come to rule 5, we will see how, say for example, if I take a pellitic rock, a mica schist, if I analyze it, what will I get? Let's all assume that the mica schist is amphibolite to granulite facies condition, or ignore it, at least amphibolite facies conditions. So the possible elements that will be there in this mica schist are SiO2, I will see it right because otherwise I might make mistake, SiO2, TiO2, Al2O3, Fe2O3, FeO, MnO, MgO, CaO, Na2O, K2O, K2O, P2O5, B2O3, C is carbon, S is sulfur. Is there anything else left? How many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Now listen. This, a typical mica schist, will have all these in the system. So this is a 15 component system. We can't handle this. It's too big. It's too big. So what we do? Let's say I want to ignore SiO2. Why will I ignore?
Because it's your face.
because SiO2 occurs as a pure phase. Rule 1. Rule 1. I have forgotten the rules, what I have. Yeah. TiO2, if there is no, there is, yes, albuminate, this is also gone because of rule 1. Let us say B2O3. I don't need B2O3. Why? Which rule? B2O3 is rule 4. What about S? I also want to eliminate it. S comes in pyrite or pyrrhotite, and it does not go with any other element. So I will put it as rule 4. If there is no graphite, then can I apply another rule? Components that occur in only one phase, even 3 or 4, either of the two. I can use either of the two. If there is only hematite, then how will I do it? Rule 1, because that's hematite. What about H2O, etc.? If this is externally controlled, rule 2. Do you understand? Manganese is not such a strong component, so I add manganese to FeO because MnO occurs in very small amount, and CO Na2O occurs mostly in plagioclase. High pressure, if you're talking of high pressure eclogites, then of course sodium comes in as a part of paragonite. But normal pressure temperature condition, I can eliminate Na2O and CO. So from this now, I cut, and P2O5 rule, I can apatite, rule 3. So from this many components now, I come to this component K2O, Al2O3, FeO. Remember this now contains FeO, MgO and SiO2, H2O. If H2O is an externally controlled system, it's also taken out. SiO2 is a pure phase, I can take it out. So you have K2O, Al2O3, FeO, Mg. So out of these 15 components, I have made certain approximation and brought it down to a 4-component system. K2O, Al2O3, FeO, Mg. And all the rules have considered the thermodynamic aspects. There can be complications, but I am saying only for simplicity. There can be complications. So now, from this assemblage, I will write this at the top. So we have K2O, Al2O3, FeO, and MgO. We have a 4-component system plus SiO2, pure SiO2 quartz, plus H2O, which means what? Externally controlled system. So this system is called KF MASH, where SiO2 is present everywhere and H2O is externally controlled. So out of that, we have now 4 components to deal with. Now I will write to you rule 5. Rule 5. So I will read it slowly, it's a little big. Rule 5. If a component occurs in 2 or more phases, comma, and one phase is common to all assemblages, comma, project the composition of all phases with the component from the composition of the common phase onto a face of the tetrahedron or some other convenient plane. I will read again. If a component occurs in two or more phases, comma, and one phase is common to all assemblages, comma, project the composition of all phases with that component from the composition of the common phase. Project the composition of the common phase onto a face of a tetrahedron or some other convenient plane. Let me draw it. We are doing a cave patch system. The formula for cordierite, I have, you plot it correctly and see. This is chloritoid. This is chlorite. This is garnet. Staurolite, and some other phases. All these phases plot on the AlFeMg plane. But muscovite, K, Al2, Al, Si3, O10, OH whole twice. You see that K is to Al ratio is 1:3. So what will happen? K is to Al ratio is 1:3. So if I divided it 4 times, this should be the plot point where you have muscovite. Where will biotite plot? You see, biotite has the formula KMgFe whole thrice Al Si3 O10 OH whole twice. That's the formula of a biotite. So muscovite lies on the here I have plus SiO2 plus H2. I don't have to repeat this every time. So muscovite plots here. Staurolite, cordierite, this is chlorite, this is garnet, staurolite, and on this side you have chloritoid, and so on and so on. All these minerals plot on AlFeMg plane. Have you understood? All of them plot on the AlFeMg plane. Muscovite plots on the KAl binary. But biotite plots inside. So what biotite plots is, biotite plots in this type of a diagram, which is inside the plane. Have you understood? It's inside the plane. So what you now do is, so your muscovite is off. Your muscovite is off, and therefore you have to plot all your elements. All the minerals are on the AFM plane except biotite. So if you have to then plot biotite, so AFM is the screen. Biotite plotting position, this is the source, and muscovite is the source, and the plotting position for biotite is inside. So what happens if I join this, and if I join this biotite will project on this plane outside. Do you understand? If I take this muscovite and plot everything else, they will plot on the surface because they are on the surface. If I take a light and say this point is here, if I take a light and point it here, it will remain there. There will be no changes. But if there is something here, you can see the shadow. If it's here, nothing will happen. The shadow will be static. But if I am here, then you see the projection will change. Your source is the same, but your projection position will be changed. So biotite, this is biotite. This biotite position would be plotting here. Why? It plots here on the AFM plane. Plots here on the AFM plane. From where? From muscovite. Say for example, if I had K feldspar, KAlSi3O8. Have you understood? So now you see, where will it plot? KAlSi3O8. Where will it plot? It will plot exactly here, K feldspar. Right? So muscovite, if you plot it from muscovite, K feldspar will plot right here. That means if you are looking from here, K feldspar will appear to plot here. If you are looking from here, K feldspar will plot behind. Have you understood? So now, if I plot things from muscovite, then I have to make certain change in composition. So what I had initially, I had K, Al, Fe, F and M. Now I have to, potassium has to go and a new Al prime plotting position will arrive. Al prime. And what will be Al prime? How will I do this? You see here. For one potassium, there is 3 aluminium. So Al prime would be Al minus 3K. Al prime will be Al minus 3K. But say for example Fe prime, this will be Fe minus nothing, because muscovite does not contain iron. So there is nothing. So Fe prime will be equal to Fe. And Mg prime will also be equal to Mg. So the point only that is here, Al minus 3K. That is only thing you have to understand. Why I have written minus 3K? Because if I take one aluminium for which 3 potassium ions, you see, for 1 potassium ion, 3 aluminium goes. For 1 potassium ion, 3 aluminium goes. So I have to I am subtracting aluminium. So I am subtracting 3 into aluminium, that is 3 times the potassium. So this is now what will come to. And so finally, your Al prime will be equal to Al minus 3K divided by Al minus 3K plus Fe prime plus Mg prime, or Fe Mg. And Fe prime will be equal to Fe prime divided by Al minus 3K plus Fe plus Mg. And what will be Mg prime? Mg prime will be equal to Mg, this is Mg, divided by the same denominator. That is the basis of your AFN projections. AFN projections. You can do it also as L2O3, FeO, MgO, it doesn't matter. These things will change, but you can do it on the elemental basis or on the basis of oxygen ion or as oxides. But the basic principle, say for example, I have done this projection from biotite. Muscovite. How will it will the biotite projection point be same if I plot it from K feldspar? Will the biotite, this was the original biotite. This is the now plotted position of biotite I have projected from Muscovite. Now, I am asking you a question that if instead of Muscovite, if I plot it from K feldspar, what would have happened? You can see very clearly, since this is gone down, it will not have the same position to plot. But how do I know which position to plot? It's very simple. Now I am doing from K feldspar, not from Muscovite. This is the formula for Muscovite. Now I am doing from K feldspar. So what is for K feldspar? KAl Si3O8. Potassium to aluminium is 1:1. So the original was KAl FeMg. That was the original. Now I'm projecting from K feldspar. How will I eliminate? So my Al prime will be equal to Al minus K, because it's 1:1. And your Fe prime will be equal to Fe. Your Mg prime will be equal to Mg. And similarly, you can do the percentages in a diagram. So, you see the plotting position of the mineral. Here it's Al minus K. But when I do it from Muscovite, it is Al minus 3K. So, it depends on if I take this and change the source. You see, here if I take the pen, depending on the source of light, it will change the position. So the biotite position, this that I have drawn, was for Muscovite, for which K is to Al was equal to 1:3. But when I do it with K feldspar, the K is to Al ratio is 1:1. And for which Muscovite will plot on this side. Because if you plot from K feldspar, Muscovite will go up. So if you're looking from this diagram, Muscovite will go off. But if you plot it from Muscovite, then K feldspar will appear going down. So that is the mainstream of AFM projection. Now you can do for ACF, AKF, it's all the same. You have to know the compositions of the minerals, what you want to project, and the source and the projection scheme. So you will have plotting positions and you will have plotting coordinates. These are called the plotting coordinates for plotting positions. So different minerals, same mineral, will plot differently in the composition space if you change the plotting position, plotting coordinates. So these are plotting coordinates and these are plotting positions. Muscovite is the source from which the plotting is done. Here from K feldspar is done. If I plot from K feldspar, biotite will appear higher because you're subtracting less amount of potassium. So aluminium will go up. Right? I think I will stop here now. Next class I will tell you about repeated, what should I say? Projecting, I project this and then I project again. We will do this, it's a little complex, but we will do it. I project a mineral from a mineral and I take that mineral and project it to another mineral, and so we can have repeated projections. Right, thank you. You can try it any bad. If you want to have a great deal of right, if you want to really have it, really to learn, the book by Frank Spear on metamorphic phase equilibria, the thick blue book. There are a lot of these projections given there. Always the derivations are not given, but it is, since it's an advanced level book, it is understood that you will be able to find your derivations. So you can try those derivations to find out. So you have ACF, ANF, NKACF, different types of diagrams to suit your rocks. Right? Thank you.